of the diverse morphologies that are seen in planetary nebulae. Now, however, these two-dimensional classifications are subject to a number of problems. First, there is orientation effects. Second is sensitivity, dynamic range. You go deeper and you see different shapes. And also you could be affected by the field of view. I'm going to give some examples there. This as old as a Messier object. So this one, when CCD observations were possible, so this simple nebula turned out to be a bipolar nebula. And with CCD, you go a little bit deeper imaging, you see a lot more bipolar nebulae. For over the last several meetings, we have been talking about what's a fraction of bipolar nebula. Now, even some of the most famous nebulae turn out to be bipolar. And with simulations in particular, with kinetic studies, one can create models. And it turns out that well-known planetary nebulae like 2392, 6543, 7009, they have all apparent very different shapes, but turn out the intrinsic shape is almost identical. So the two-dimensional classification is not a necessary indication of the three-dimensional true structure. So now, as already been mentioned, we now have more complicated things. We have multipolar nebula, which is already well established. There are many examples, even famous objects like NGC 2440 turn out to be multipolar. And there are many examples have been indicated by Nobusoka that you can see pairs of bipolar loops. And well, I'm not going to have time to go into the physical origins of these structures, but probably they have to do with either simultaneous ejection into different directions or episodic ejections. So we are talking about time-dependent, directional variable, and coordinated outflow. So it's more complicated than the spherical symmetric stellar winds that we know for a long time. So now again, on the right is a JWST recently released image. And as a matter of fact, is a well-known nebula, NGC 7072, 4072, 6072, already known to be multipolar based on the infrared colors. So again, another example of well-known planetary nebula, 7026, also multipolar. So the question is, what is the true fraction of multipolar nebula? So it range from Manchado's estimated of 12% to so high as 20%, but they are most likely underestimates. Because if you try to you create a very simple model, a single unified model, and you rotate this nebula into different orientations and then see to it, set to different degree of sensitivity, they can create a large variety of two-dimensional morphologies that you can see here. So when they on the top row of it are the actual images, on the next row are the simulated images. So one single three-dimensional model can create many different two-dimensional morphologies depending on the sensitivity level and orientation. So again, many of the discussions in the past meeting have focused on when does this bipolar or multipolar shifting take place. So after the discovery of planetary nebulae, you will hear more about them in this meeting. Then we know that these bipolar or multipolar structures are already seen. So the whatever shifting or due to coordinated outflows and so on probably happened right after the asymptotic giant branch. Now, furthermore complicated, there are these kind of recessive type of outflows extended to very large a degree over the sky. This one is 1.5 minute, framing one, and this kind of spirals now we know, and we'll hear more about in this meeting. They can be imaged in the envelopes of symbolic giant branch stars, these spiral patterns. So are these spirals related to these precessing flows what we see in the later part of the planetary nebula evolution? So this link still yet to be established. I mean, the most famous example, again, the spirals in N29, where consecutive imaging showed the movement of the spirals. So next, I want to move to episodic outflows. We have evidence for that in terms of the concentric arcs. These are seen in planetary nebulae and protoplanetary nebulae. They are most likely projections of three-dimensional shells. And there are also two-dimensional rings. So these rings are perpendicular to the bipolar axis of the nebula. And you can see in Hubble 5, for example, NGC 6881. So this is a whole series of two-dimensional rings. Now, the interesting thing is that we all know about the famous letter structure in the red rectangle. Now, by simulation, you can construct a model of the red rectangle and turn it around, and it looks exactly like Hubble 5. So the ladder has become the two-dimensional rings. So again, this means there's some kind of a cavity being driven out of the circumstellar nebula, probably in the episodic manner, creating these two-dimensional rings. Now, these again, the microstructures have been known for a long time, in particularly the Helix nebulae, since the HST have imaged them. So with this JWST, more and more are also being seen. This another now, Sahai probably going to talk more about this. We also have these high-density knots in collimated outflows. So what is the origin of these knots? So again, some kind of episodic phenomenon. The good thing is that with genetics, we know the intervals between the knots, and therefore we put constraints on whatever model that create this episodic phenomena. Now, well, I'm going to say a bit more about infrared imaging. You have well-known nebula here, but you take a infrared image, then you see a bipolar structure. So the optical pathology is not a reliable indicator of the morphological shape of planetary nebula. So another example of a bipolar nebula is discovered in the electric tape planes away by the Spitzer telescope. And more examples of these bipolar nebula. So in the optical, you probably never guess this is a bipolar nebula. Now, another thing is field of view. Now, we are usually only interested in the wider part of planetary nebula, but if one have the luxury of taking a wide field image, then you discover they may have outer structures. So again, in this example, you have a pair of bipolar loops way outside of the main optical nebula. So now this extended over arc-minute scale. So here again, these bipolar loops can be seen when you take a larger image. Now, Alberto Lopez have made studies of many different kinds of large bipolar structure, and they sometimes have also this spiral structure. So these are these planetary nebulae? How can these bipolar things being so big? I mean, we don't know. Now we also know that most of the mass in Planetary Nebula is not in the ionized region because most of the energy is coming out in the infrared. Now infrared imaging, you can take a look. I mean, the well-known bipolar nebula, you can see that the infrared component is concentrated along the waist. So in Planetary Nebula, you can do 20 micron imaging. You can map the torus region. Then you can compare the orientation of the torus to the orientation of the bipolar loops. Now, the key thing is that these big bright nebulae actually are confined by unseen matter. The unseen matter not only in torus, but also on the outside because of the very short boundaries of the object. So all these things are very short boundary, meaning that they are really cavities. They are not avenues of mass ejection. They're all confined by external material, which can only be mapped in the far infrared. And our only good example we have is 2346, where you can see in the far infrared going to 160 micron, that you can see the spherical component of the coal dust. But our present capability, even with SOFIA, are not good enough sensitivity, the brightness sensitivity, to pick up the external unseen component. Now you can see the optical structure may seem complicated, but from the infrared is clearly just bipolar. Okay, so now of course now we have ALMA. We can map the molecular emission. You probably again hear more about it in this meeting. So we have a massive molecular torus constraining the outflow. Now the key thing is that although the optical nebula is very attractive, very bright to the invisible light, but actually they don't contain most of the mass. So most likely they are cavities, low density cavities being cut out by collimated outflow, and because they can radiate strongly in recombination lines and collisionally excited lines, and we are attracted to them because of their brightness. But most of the mass are probably outside of the nebula. So we have short boundaries of many examples, and they have bound by unseen matter. Okay, so bipolar loops are not regions of mass ejection, but low density cavities cut out by collimated outflow. So, okay, so well, I have to hurry up here. Okay, now we of course we now know there are many binary central stars. So how do they relate to these morphological features that we are talking about? And from Bruce Ribnak, he will talk more about how his studies of the planetary nebulae, binary stars, how do they relate to planetary nebulae? So the key question is that if planetary nebulae is some kind of characteristic variable, then we have to define on what branch of the CB evolution that they belong. So as this field is a very old one, there are many people who've done extensive studies on binary star evolution. They have hundreds of branches of evolution. So if we are serious about binary stars playing a role in planetary nebula formation, we have to identify where do they fit in the characteristic variable evolutionary branches. Okay, so again, common envelope ejection. After common envelope ejection, would the star evolve? If they don't evolve, do you still call it a planetary nebula? So it comes to the question of what is the planetary nebula, and Quentin Parker will talk more about that. And we know that we have a lot of problems confused with other stars, and the most common example is symbiotic star. We now know a nova is a star evolving backwards. Symbiotic star is a binary system which is not evolving. So So what is a planetary nebula? A planetary nebula, well, I think we have to have more than a definition, more than observation. It has to have some degree of a definition based on evolutionary status. I don't have time to talk about this. So we have a lot of unexplained phenomena, and we need, for example, integral field spectroscopy to better determine the kinematic structure of the nebula structure, so that we can build a three-dimensional model. And back to you. Thank you, Albert.
Thank you. Well, an exciting start to the meeting. Are there any questions? We've got a couple of minutes for questions.
Yeah, I think definitely it's very important to have the mathematics in account,
Yes.
because sometimes what you see on the plane of the sky is not the real structure. So,
Yeah, integral field spectroscopy.
that's the best. Yeah.
That is the way.
Vincent?
Thank you very much for this avalanche of data. You've just simply given the images. If you were to give your talk again, just talking about the observed velocity field, what would you get?
Oh, well, it's so complicated. I mean, well, we don't, I mean, we have to rely on the other people to give a satisfactory answer. I didn't have time to present any kinematics. Like, for example, Alvaro Lopez have done well with it's just a spectrograph and map out a lot of kinematics. And I think these are the, like Martina said, is really the key to have a three-dimensional picture of what's going on.
More questions?
Yes, do you attribute the non-spherical structure to the definition of a planetary nebula? The sun will not form a planetary nebula?
Well, I would like to say that whatever observational definition, we have to put in a theoretical definition. Say, for example, is an object which is evolving from, say, the symptotic giant branch to the weight of stage or something, to distinguish between similar objects like novae and symbiotic stars, which are evolving differently.
So should I say that even much more than looking to the spectroscope
Yes.
in the optical, you should go to the infrared, even near infrared spectroscopy, because most of the data is there.
We need kinematics from millimeter wave, which is easy to do now, except the sensitivity is terrible. I mean, in front does, but in the optical, we can do pretty well. Yeah, and of course, whatever line you can have, yeah.
I don't know if you could come up to these. It seems to me that the question now is a planet nebula a special case? Or do all stars in the right mass status take one? With so many parameters, what will happen? What's your answer?
We don't have it yet. It's a complicated question. We have to be careful not to, we have to have a definition. But I think Confucius have said you can't talk about any subject until you know what you're talking about.
Thank you very much.
Yeah, one comment, if you want to keep the discussion alive, you can go to the science channel of the Slack. So you put the questions and comment on the slide and reply on there, any particular question. What is the
Okay, so next question is Surendra Saha. He will talk about this new evolutionary channels.
Thank you. Well, first, thanks to Martin and the SOC for organizing this very, very exciting meeting. Thank you all for coming. So I'm going to be talking about investigating a new evolutionary channel for dying stars. My collaborators here are Geeta Sarkar, David Akamet, Mike Ressler, Hans van Winkel, who should be somewhere in the audience, Stacy Bright, and Ryan Lau. So the first and best studied example of this class of objects in our galaxy is the Boomerang Nebula, which also happens to be the coldest object in the universe. It's so cold that it's actually the expanding matter is below the microwave background temperature. Here's an HST image on the left-hand side. You can see a beautiful multipolar bipolar/multipolar image in the object in the center, and surrounding that is an extended shell seen scattered light. This object has extreme mass outflow properties, the mass loss rate of 10 to the minus 3 solar mass per year, a very high expansion velocity. The ultra cold envelope, this very cold envelope, is very, very large. The ratio of 12C to 13 carbon is very low, close to the equilibrium value which you can get. But the most important thing is the luminosity is only about 300 solar luminaries. So this cannot be a AGB, post-AGB object. On the right-hand side, you see the ALMA CO2 image overlaid on the HST image. You can see the beautiful structure in the center very clearly. Okay, so this class of dusty post-RGB stars. Well, as I said, the Boomerang Nebula is the best studied example in our galaxy. However, about 120 dusty objects like these were discovered in the LMC and 45 in the SMC. They were identified as post-RGBs based on the spectroscopic determination of the effective temperature and the log G by Devika Kamath and collaborators. Now, finding post-RGBs among dusty evolved objects in the Magellan clouds is much easier than in the galaxy, especially pre-Gaia, because there is no distance ambiguity. That enables a reliable luminosity determination. So from this spectroscopic study, the Kamath et al. Were able to determine the effective temperature, the log G, the metallicity, but the most important thing, they found luminosities were lower than what you'd expect for an AGB object, less than about 2,500 solar luminosities. And the spectral energy distribution of these objects show evidence for circumstellar envelopes, shells, and disks, which are similar to what you see in post-AGB objects. Okay, so here's a HR diagram to tell you where these objects sit. So you can see the red dots, the red symbols are objects in the LMC, the blue ones are objects there in the SMC. The cyan region is the main sequence, and what you can see so you can see that the luminosity range covered by these objects, the post-RGB objects, is pretty low, as I said, about 2,500 solar luminosities. And that means that they must have evolved off the RGB along these tracks, these multiple different tracks, for different final solar central stellar masses. So the post-RGB tracks, the final mass is less than about 0.4 for solar masses. The post-AGB tracks, of course, are more luminous with a final mass greater than 0.44 solar masses. Okay, so what can cause this premature termination of the RGB? And the second question is, what can produce infrared excess? Well, the answer to the first question, the only possible explanation that we can think of is that these systems are a result of a binary system, and there was a compound, and there was some violent binary interaction on the RGB leading to an ejection of the envelope on the RGB itself, and therefore the star then went on its post-RGB track towards higher temperatures. Now, the details of the compound envelope evolution, which have been studied by a lot of theoretical authors, is complicated, and there are various flavors to it. For example, the common envelope ejection does not have to be in one go. It can be episodic ejection with ejection of about the 10th of solar mass every few decades. In addition, the disk can form due to partial fallback of the ejector. Another possibility is that the in-spiral phase of the binary of the companion replaces the role of stellar evolutions, which you see, stellar pulsation, in AGB stars, and that leads to an expansion of the common envelope beyond the condensation radius, and then you get an efficient mass loss through a dust-driven wind. So, though you have common envelope evolution, the ejection is not due to the gravitational potential energy, but it's due to the kind of winds which we see in AGB stars. Okay. So what we did was to carry out some modeling of the post-RGB objects which had been found in the Magellan clouds. Kamath et al. Classified these sources as shell type, where the spectral energy distribution peaks at greater than 10 microns, and this type where the spectral energy distribution peaks at less than 10 microns. So we selected a sample just as for this study of 4 shell type and 4 disk type post-RGBs with luminosity less than 1,000 solar luminosities, and 4 shell type and disk type post-AGB objects with luminosities greater than 3,000 solar luminosities. The SEDs extend from the U band to about 24 micron in each case. What we used for the modeling was this 1D Dusty code. Now, however, so I'll explain in a moment how we managed to do the disk as well with the 1D code. So we have a disk component and shell component, and the free parameters are just temperatures and the radius of the shell and the disk, the thickness of the shell and the disk, the wedge fraction, which is the opening angle of the disk, the optical depth of the shell and the disk, and dust grain size and composition both in the shell and disk. Now the disk is approximated as a wedge-shaped fraction of the sphere, and I'll get into. People can ask me questions of how we actually did this, but we used a simple code in order to do this modeling. So here's an example of two objects that we modeled. On the left-hand side is a one-component model, and you can very clearly see that it doesn't do a good job of fitting this region. But however, if you go to a two-component model which has a shell and disk, you can see you get a much better fit. Same thing happens here for this object. So the simple classification into disk and shell source from SED shape is not accurate. We need to do this kind of modeling to determine whether two components are necessary or one component can do the job. Okay, so here's a summary of the important parameters that we derived for these set of objects. I won't go into details except to point out that so these are the shell sources, these are disk sources for the post-RGB objects. And you can see that the total mass of the disk is quite small. But the mass in the shell is larger, but it's still quite small compared to what you would expect for the total mass that needs to be ejected, half a solar mass or more in order for this object to be going on a post-RGB track. I'll come to that in a moment. So other important results are that the ejected matter in some sources we found is carbon rich. At least as carbon-rich content, which is very surprising because on the RGB you don't have the nucleosynthesis necessary to produce excess carbon. So it's a question: how do you get carbon-rich objects? So at least for a couple of objects, we see in order to model the SED best, we need amorphous carbon in the disk, and the shell we need silicates plus silicon carbide. There's also a discrepancy between the model observed SEDs in some sources in the IRAC4 bandpass, which are at 8 microns. That suggests that there will be 7.7 micron pH emission contributing. So again, where do you get pHs in these objects? Again, as I said earlier, the shell masses, the total mass, which is dominated by the mass of the shell, is very low compared to the mass that must be ejected for the star to lose its stellar envelope and proceed on the post-RGB track. Okay, here's a theoretical study done of the inferred circumstellar dust mass for post-RGB sources by Liu et al. And so the heavy curves here are the curves of what you would expect if the ejection happened on the base of the RGB, and the thick curves are if it happened the thick curves are if it happened on the base of the RGB, and the thin curves are if they happen on the tip of the RGB. So if the ejection happens on the tip of RGB, you get much more dust forming in the ejector. And the colored lines are the plots of our post-RGB sources from the study which I just described, and these are all lower limits. And so you can see that we conclude by comparing our inferred ejected dust masses with the study that most probably the common envelope ejection occurred near or at the tip of the RGB for the source that we studied. Okay, now modeling the SED is good and interesting. However, we really need spectrum. For example, here are two best fit models. Oh my God, really? I always remember. Okay, so well, I'm going to hurry up now. So what I'm trying to say here is that we really need spectrum to distinguish between models. And we, in fact, JWST to the rescue. So here's some preliminary data from an archival program. Well, it's archival data now, but it's a GTO program. Here's a post-RGB object in the SMC, and you can see this beautiful bipolar nebula. Here's a spectrum, and you can see it's dominated by molecular hydrogen lines. And in addition to that, you see this SIC feature. So clearly, the spectra confirm what we are seeing from the SED modeling, that you can have carbon-rich dust. Here's a simple plot fitting the temperatures of the molecular hydrogen lines, and you can get a fairly nice bit with two temperature fit. An important thing is that a lot of the mass is actually in these bipolar lobes, which is not included in the SED models which I presented before. So we have to include that as well. Now I'm going to come to what we can do with other observatories. So the HST observations of the scattered light can really help. For example, here's a model of the pre-planetary nebula that 1-92, and a model of the scattered light tells us that there's a mass of about 1 solar mass in this sort of torus-like structure. Here's what the Boomerang Nebula would look like if it was at the distance of the NMC. And basically, we can, if we got HST images, we can actually resolve the post-RGB sources, which are even about a third of the size of what you see for the Boomerang. Now, the important question is, where is the missing mass, right? So, sorry, this is incorrect. This should go with 3 solar masses, and this will be 45 degrees Fahrenheit. Anyway, there are 2 objects here for which we have Herschel observations in the far infrared, and it clearly shows that these are our models of the SED up to 24 microns, and then this is the model of the additional component that we find from the Herschel data going up to 250 microns. And clearly see most of the mass lies in this structure, and these structures are of course much larger than the structure of the disk emission that we studied. So the answer to the questions I asked earlier is that most likely all the mass lies in these extended shells, which are far away from the central sources. Now, we can probe these far infrared things with this mission, which we hope will be accepted later on. It is called CLIMBER, and the Zephyrus is an instrument of top in that it does spectroscopy. And here this table shows that, you know, in a small amount of time, we can actually get fairly good signal noise ratios of the emission at these long wavelengths. ALMA observations are very useful for probing the gaseous component. For example, the mass of the ultrapole ejectors compared to the Boomerang Nebula, you could clearly see it within a reasonable amount of integration time. An important thing would be to also measure which you can do with ALMA, is to measure the 12 carbon to 13 carbon ratio, which should be relatively low if these are post-RGB objects. Okay. So I won't go into very much into detail on this, except to say that we really need, in order to study these objects properly and model them properly, we need a RAD-MC 3D, which is a 3-dimensional modeling code. And then you can put in, a central disk, the lobes, and an extended shell-like structure in order to determine the physical properties of these systems properly. So again, I've already said this, so I'm just going to we need JW spectroscopy, and thankfully we have the time now for at least about 5-6 objects. We have HST imaging, which you would like to get, PRIMER, which will come along in about hopefully in 8 years or something, for far infrared observation to detect the missing mass, and ALMA millimeter wave observations to determine the mass of the gas. And as I mentioned, we need good modeling to model all these things. And I'll leave you with my conclusions here. And thank you very much.
Thank you, Dr. You finished 1 second, I think, before you know. Perfect time, Peter. Question at the back. Arturo?
Yes, because the way most ADV are selected for their infrared excess, there is some contamination of young stellar objects. Can you take that into account?
Yeah, so no, that's a very good question. In fact, in the papers, the Kamath et al. Papers that I mentioned, they used log G as a discriminant between. So if they were YSOs, they would have to be relatively massive to have these luminosities, 4 solar masses or more, and then the log G values would be significantly lower than the log G that they determine from the study for the post-RGB candidates.
Yeah, but the young stellar objects don't have very low luminosity.
Sorry?
Young stellar objects may have very low luminosity.
Right, but we are looking at objects which are 1,000 solar, 600, 700 solar luminosities or more, and so in that bunch of objects, if you have a object which is a YSO, then it has to be relatively massive to have that kind of luminosity, and therefore the log G has to be relatively low.
Okay, thank you, Joe.
Mark Under, these are lovely results, and it's nice to connect the post AGB with the post RGB. So a comment and a question, you can also, I think, go higher in mass and get to the bracket E supergiants, B bracket E supergiants, with essentially the high mass extension of the post AGB class. So that's sort of the comment, it gets us into interesting massive star regimes that might be of interest to many. The question is, this missing mass is a longstanding problem, as you well know. Is CO the right way to go at it? Is Prima the right way to go at it? Is neutral carbon lines in the submillimeter the way to go at it? What do you think?
Well, for sure, if we had far infrared, that's the way to go, because the place where we're going to see the extended dust is going to be relatively cool and seen in the far infrared. At that radius, the CO is all photodissociated. So CO observations will detect stuff which is much closer. Neutral carbon is a good bet. So, that's the way to go about detecting maybe, once the CO photodissociates, you have neutral carbon. So, yeah. So that's doable with ALMA, yeah.
So,
Could you elaborate how can a post RGB object be carbon rich? It's no carbon
Right, so,
synthesized.
yeah, so that was one of my slides. I didn't go into that, but okay, let me. So this was actually something that Jura discussed, and we basically agreed that there are two possibilities. So one is that the companion was a carbon-rich star in the past, and now it's a white dwarf, and that polluted the primary's atmosphere. Okay, so that's very, very simple. That is also, of course, an explanation of dwarf carbon stars, which we know exist in our galaxy. The other possibility is that during the mass transfer and the compound of ejection, there are physical conditions which can produce like pHs and SI, maybe SiC as well. So again, SiC has not been discussed in the paper by Jura, but pHs have been discussed. So anyway, I'm just throwing it in. Maybe you have basically you have to photodissociate CO to get, not photodissociate, dissociate CO to get carbon, and then you can make carbon-rich dust. Yeah.
Just a comment. Remember that interstellar medium is oxygen rich, and it's plenty of pHs.
with no silicon carbon.
Yeah, that's true, but there's a solution for the pHs.
Yeah. Okay, well, I think we're finished on time now, so we need to move on to the next speaker. There is a lot to discuss though, like, do these things make planet, and we never got. But we'll come to that. Okay, next. Tell us what isotope ratios and
wherever. So this is. Okay. Oh, well, thank you very much for inviting me to give this third talk. It's supposed to be the third introductory talk, but I'm not introducing anything but about problems to the field. This is about isotopes, but trying to understand planetary nebula shaping, which is the reason I'm here. But I will focus on determining masses. That's the basic idea behind the project. Before going into the details, just want to introduce a few namings. Maybe you won't agree with me, but I will talk mostly about not planetary nebulae, but the stage before the preplanetary nebulae. And in that terms, we have two kind of sources, although of course, all sources are biased, and maybe this classification is not 100% complete. But we have something that I like to name as low momentum sources. These are these kind of sources that Hans Lambinkel and Ivan have been studying. They are binary post-AGBs with some post-RGB contamination. They are all binaries. They all have a main sequence companion. This main sequence companion is launching a bipolar jet. They have a disk in rotation. So you have all the ingredients to launch jet and explain bipolar things. They don't have excess momentum. So we don't need all these elements. They are poor in molecular content. There is missing man problem. I mean, the amount of mass you detect is not enough to explain to be either in the post-RGB or post-AGB. And you have few examples, and there are a few. There will be some talks by Hans and Ivan on those objects the next days. the other kind of object, I will call it the classical high momentum sources. They are all bipolar, multipolar, whatever. They are supposed to be binary resistant. We don't see the binary yet. We are looking very hard for finding a rotating disk so we can launch it. And except for the case of OH231.8, there are no signature of rotating disk in this object whatsoever. They are rich in molecular content. They don't have mass missing problem. You can find up to 1 solar mass in these envelopes. So that is your explanation for being in the post-AGB. They expand fast, they have huge energetics, and they have momentum problem. You cannot explain those things via radiation pressure, so we need something else. And there will be many talks on this kind of objects in the next days. Okay, the main interest is, can we weight the progenitors of post-AGBs or planetary nebula or whatever? Of course, you can measure masses by doing some modeling, but for that, we need to have good distance estimations and get rid of the reckoning, all the stuff. And in the case of preplanetary nebula, this is not easy because they are very obscure. And in fact, it has been a work published very recently. There is a catalog of only 69 post-AGBs with diabetes. And if you have a look at those, there are only 24 sources in the Northern Hemisphere, and just 10 sources have been observed in CO. So in terms of knowing the mass and all these properties, there is little known on these characterized objects in terms of mass as derived from stellar evolution models. We can try to estimate masses from binaries. You need to find the binary, but I just want to point a talk by my colleague Pedro Pablo Campo, who is going to talk not on post-AGB binary, it's on error query, but you will see the difficulties we have if we have determining masses even when we know the orbit of the system. So the idea was to rely on stellar evolution models and nucleosynthesis models. And we know that because of the third Dirac events, when you are in the thermal pulsating AGB, you start with carbon 12 to carbon CNT ratios given by these black dots. And by the end of the AGB, you have a 12 carbon enrichment for a range of meshes. You have also the same trend in the carbon to oxygen ratio. And there is interesting ratio, the 17O to 18O, that doesn't change very much along the AGB. So that's something that can use even to weight AGB stars, because the ratio you get is independent of the point in the AGB evolution you are. And this has been done in the past with rather successful results. So at some point, we decide to go and try the same with post-AGBs, because in the case of post-AGBs, we already know that we are going to be in this position in the abundances predicted for by the end of the AGB. So we can compare masses derived from the 12 to 13C ratio, to 70 to 18O ratio, and even to the carbon to oxygen ratio. So we can compare all these three things if we manage to do that, and see whether all these results are consistent. Since I'm mostly a radio astronomer, I must tell you that we radio astronomers, we are not very good at determining directly the numbers of the carbon to oxygen ratio. We can infer whether carbon is more abundant than oxygen based on some molecules we detect. If the standard chemistry holds for these post-AGB sources, which may not be the case. But we can determine this 12 to 13C ratio, but because of the 12CO may optically thick, and even sometimes 13CO is moderately optically thick, we need to do a very good modeling for that. What we can really determine pretty easily is the 16O to 18O ratio based on the CO molecules, because these two are optically thin, and just by dividing the two intensities, you roughly get the abundances. So I'll focus on this thing. Before we start the project, the situation was this one. This is the range of, this is the curve you expect for the ratio. This is the range of masses for oxygen rich. So you expect to have 16 to 18 O ratios below 1. This will be for carbon rich, and this will be for stars heavier than 4 or 5 solar masses. That depends on the metallicity, where you have hot bottom burning. And one of the results of the hot bottom burning is that you become enriched. But again, this ratio becomes tremendous. It goes really to hundreds or thousands. So you shouldn't detect 18 O species in those guys. And the situation was rather confusing because there was this paper by Theo in the room who studied water fountains that are all oxygen rich, and they got this range of values from well in the carbon rich range, but also in the oxygen range. And we already studied that carbon rich. This is one of these low momentum sources, which is carbon rich. We thought it was carbon rich, and the ratio is well in the range of the oxygen rich. So nothing did make any sense. So we did a couple of projects. I was leading the project with the Northern Sources with the 30-meter, and Theo submit, and he's still submitting ALMA proposals to trying to get up to 40 targets in the Southern Hemisphere. So far, only 6 have been done. I'm going to present the result from the 30-meter. Theo is going to present on the last day the result from the ALMA survey. One important thing from our 30-meter survey is that we observed 13CO, C16, 17O, and C18O at the same time with the same band, with the same calibration, almost the same beam. So if anything goes wrong, it goes wrong the same way in all 3 transitions. And just by applying this number, well, this is a roughly estimation, but applying this number for compact sources or this number for point sources, from the intensity ratio you directly derive, by correcting by this factor, you derive the abundances, provided that there is no selective photodissociation effect or chemical fractionation that we don't expect to have in this weak stuff things. We observe up to 15 sources, mostly protoplanetaries, a few planetaries, and some other sources for control. These are a few of the examples. For example, this is Frosty Leo, is a well-known oxygen-rich. Why is it oxygen-rich? We have pretty strong SiO lines, weak HCN lines, and most important, SO. SO, if you detect SO, that's for sure an oxygen-rich source. And the ratio is, you have more 18O than 17O, that's fine. But in this other case, we don't have SO, we have SIS, that this change means that this object is carbon rich, pretty strong HCN lines, very weak HCO plus, very weak SiO, so this is a carbon rich, but again, 18O is stronger than 17O, which was not expected. Same happens with this IRAS 22272, and on the contrary, this CRL 2688, this protoplanetary, is carbon rich and behaves as you expect to be for a carbon rich, so with more 18O than 18O. These are the summary of the observation sources, the lines what we have detected. The ratios, the one in red, are not what we were expecting, so they are the other way around. And this is more or less the summary of the results. This is the box of the oxygen rich. I don't know the masses. I am not saying that this guy over here will have a mass of 0.8 because this will be the prediction. I'm just saying this. This goes into the box of the oxygen rich. This goes in. This is the box of the carbon rich, and this is the hot bottom sources. And the height of the object is the actual measurement of the oxygen 70 to oxygen 18 ratio. So these are the normal oxygen rich. You have 18O more abundant than 17O, and you have an oxygen rich chemistry, so fine. But we also have those sources which the ratio is reversed. and they are still oxygen rich. My explanation for that is that you have an interrupt evolution since the oxygen ratio is set at the beginning of the AGV and you become carbon rich after you end the AGV. If you somehow get interrupted, you can remain oxygen rich while having this ratio characteristic of carbon rich. Then you have the normal carbon stars, but you also have this kind of stars which are carbon rich, but have ratios typical of oxygen rich. And for that, I have no explanation. And more surprisingly, we don't find sources where we always detect a C18O, meaning that either this prediction is wrong or we don't find sources above in the range of the hot bottom warming gene. This is even more complex because now Ivan is going to talk about this source. We said it was carbon rich. Now it has been detected with all its measures, so maybe it's oxygen rich. But according to this catalog of Gaia well-observed sources, it has to be a mass of 3.1 solar masses, so nothing agrees. Same happens with this one. The solar mass must be much higher, so maybe it should be carbon rich. I don't know. This is okay, no grounds, but this should be massive, but it has this ratio very low, and based on this the belonging to this cluster, this object has to be 3 solar masses, but then this ratio doesn't make any sense and should be carbon rich too. So, and this one is a yellow hypergiant, so it's a post supergiant with hot bottom burning, and still this ratio is pretty low. So probably I'm not solving anything. I'm just maybe nervous, but we need to do something. I guess we need to check metallurgy but of course for this very obscure object that will be tricky because these curves change with the metallicity. We probably need to find at least some hot bottom burning source. And we need to determine whether these carbon resources are reaching 12 carbon or all kind of carbons or whatever. And also determine whether all these objects that were supposed to be carbon rich at the end up being oxygen rich are all the result of interrupted AGV evolution. And that's about it.
Thank you. The first question already, Sarah?
Thank you for the presentation. I have the question because I think I missed something important. What does the initial mass in this diagram come from?
The initial mass, I mean, you can predict the initial mass if you trust this curve. Well, this curve depends on metallicity, the details depends on metallicity, on many things. There are different models, but there is roughly this curve.
But that curve is the initial mass to the.
Then if you get this ratio, you just move this name over here, and you will get the mass down here. But I'm not pretending. I'm not saying I can compute the mass with that. What I'm saying is that if an object is oxygen rich, it must be in this range of masses, and it must be in this range of oxygen isotopic.
Okay, so you're only basing this.
I'm putting big boxes. Yeah, and if you're very out of the box, then you have a problem. Okay, the color boxes you are fine. You're in the color boxes. You are different. You are different. Yeah. Well, they are all different. There's another way of being different.
Any more questions?
Theo.
Yeah.
Thanks for this very nice talk. Thank you.
Hello. I was wondering then when you gave these initial masses based on the Gaia measurements,
Yeah.
that's based on the luminosity then. And also
This is a paper that has been published. I'm collaborating with these guys. Arturo is in the room. Can give more details. Yeah.
but is it based on the luminosity then, or?
Yeah, it's based on the luminosity corrected for the reddening and stellar evolution models. And as you see, the few objects where we can check both things, because they are pretty faint. Well, that's another story because they are probably CO deficient, at least some of them. So maybe this sample is not representative of the whole population of ppm. But anyway, the few that I have checked, the mass from this catalog and the mass from the oxygen ratios there is one agreement and there are two disagreements. There are only 3 examples out of the catalog where we can do that correctly.
Bill?
Javier, is it possible to summarize the wonderful mess that you presented us with? Just by saying that we still don't understand convection?
Exactly. Or else, maybe.
If I can make a comment on that, hot bottom burning is not constant along the ACP. And if you go to the end of the evolution, it turns off again. So Sarah can crystal become carbonates at the very end after hot bottom, hot burning phase. So that is not a one-to-one evolution. We use single star models for the
that's
chemical evolution.
That's the point. This is based on nucleosynthesis for single stars. So you know, maybe that's an apply here. But you know, who knows?
And the same is one time. Any more questions? If they're not, I think people are desperate for the coffee. There are supposed to be 3 poster talks. Then we moved to the first session of the afternoon because we had 1 talk drop out. And so that means we can still have coffee at almost the scheduled time.
Yes.
Martin looks very grateful.